and welcome to episode 7 of Q for Problems. Today we'll be looking at problem 7 from the Project Euler problem set, and it wants us to find the 10,001st prime number. So let's have a look at the solutions. So the problem wants us to find the 10,001st prime number. So the best way to approach this is to create a general function which can find any position number. So if I give it 10, it will give me the 10th prime number. In previous episodes, we've seen a function that I've used to generate the primes up until a certain number. So if I give it 100, it would generate all the primes up until 100. But we're wanting to do something slightly different here in terms of generating the actual a number of prime numbers rather than the prime numbers up until a number. So we're going to create a different function to do this. So what we're going to do is create a prime number test, and the prime number test will check if a number is prime. If it is, it adds it to a list of primes so far, and if not, it will go on to the next number. And then we will continuously do that until we've hit the number of primes that we want. So I'm going to start here with, say, a prime number, x equals 997. So this is just to visualize the solution. So the first thing we have to do is the special case of x being less than 2. So if x is less than 2, it's not prime because it's going to be 0 or 1. So we can just return straight away. So in that case, we would return false. So return false. So the next thing we want to do is check if x is in the first few prime numbers. So if I say the first few, so the reason for doing the first few here is because a lot of numbers are going to be divisible or prime factorized to give these numbers. So this actually gives a big speed up in terms of performance whenever we check these basic primes. Of course, we could add more to this, so we could go to 11, 13, but if we need to draw the line somewhere, so I think reasonably the first 4 here is okay. So we check if x is one of these numbers. If it is, then obviously it's prime because it's one of these 4 prime numbers. We also then want to check is x divisible, evenly divisible by any of them. So what we do is x mod p. So this will, if I run just this part, you can see that gives us a list for each of these numbers, what the remainder is. And then we want to just check, was it divisible by any of these? So we just say is 0 in this list, i.e. it was evenly divisible by one of these primes. So I run that, and that will give me either if it's true or false. So of course, if it's false, which case it's not divisible by any of these primes, we then go on to our final check. So the final check is goes with the note that any number, any prime number above 3 can be written in this form. So it's 6k plus or minus 1. So for example, so k here is 1, the numbers 1, 2, 3, etc. So for example, 1 would be 6 times 1 is 6, then plus or minus 1 gives you 5 and 7, which are 2 prime numbers as we know. Now, that's not to say that any number of this form is prime. For example, if k was 4 here, that would be 6 times 4 gives us 24, plus 1 is 25, which is not prime. So we still need to check these numbers to make sure they're prime or not. So what we're actually going to do here in this first solution is to generate all these numbers and then check is our x divisible by any of these numbers. So even though we'll get some numbers that aren't prime here, it's still going to work because it shouldn't be divisible by a non-prime anyway, as well as the primes. So to generate the list of numbers like this, we can easily do this. So we'll start off with minus 1 and 1, and then we're going to plus each of the right, and we only need to go up until the square root of the number we're checking, and the square root because we'll always find a prime factor below the square root. I've discussed this before in previous videos, so check them out if you want to see the proof of that. But Yeah, whenever you're dealing with primes, you're usually always checking up until the square root of the number you're checking. So this is a function, or this is the predicate that checks is what we've generated up until the square root. So as soon as it goes larger than the ceiling of the square root, um, this is going to stop. So this is using the while form of over. The actual function itself is just 6 plus, so we're generating essentially these sixes, and we're going to start at the number 6. So if I run just this part, um, I run just this part, you can see that gives me the multiples of 6 up until the square root of 997. So if I just run that, that is 32. So it actually gives me one more because you'll get the last one before it stops. And then we're just plus and a minus 1 from each of those. So if I run the whole line, you can see there I get for each of these numbers. So the first row here is 6 plus or minus 1. Second row is 12 plus or minus 1, etc. So then what I need to do is check that our x is not evenly divisible by all of these numbers. So I can raise this list. As you can see, it's right now it's a list of lists. So I want to have just a flat list of numbers. So I raise it, and then I do x mod again, and this gives me the remainder. And I want to make sure, I want to check that they're all non-zero, and I can just use the all keyword. And if they're all non-zero, as you can see here, true, that means it is prime. So putting all this together, I can create a function is prime. Now this function only works on a single number at a time, which is the drawback, and especially when you're working in a vector language like Q, but it's still quite useful. So we'll say, yeah, so if it's x less than 2, we just want to return false straight away. Then our next check will be x, this one here in P in our list of primes. So if it's in that list of primes, then we want to return true because it is a prime number. Then we need to check, is it divisible by any of these primes? If it is, then we want to return false because it's not prime, it's divisible by one of those numbers. And then finally we add this line, which is our final test, and it will return true or false. So all the preceding lines are essentially just kind of a performance speed up. They check the basic kind of numbers, and then this is the final check then. So if we define this is prime, and then run is prime 997, and on that you can see that's true. And if I say 100, which is not prime, you can see it gives me false. So we can use this function now as our test to actually generate a list of primes. So what I'm going to do is just copy in the function that I'm going to use, and then I'll step through what it's actually doing. So this is again using the while form of over. So we're starting with a list of just 2. So this is just one take 2, which just creates a list of the number 2. So you can see it's just a one element list of 2. And this is our starting point because we know this is the first prime, and then we're just going to keep appending to this list. So what the function actually does is it will check if the last element in the list, so that's the one we're concerned with, is the very last one so far, is that prime. If it is, then we append to this list the next number, which is just the last number plus 1. If it's not prime, we have to first remove that number that wasn't prime and then add the next number. So similar to what we were doing here. So I can actually just run this part on its own first, just to show what's going on. So if I run this, so you can see that gives me 2, 3. So now if I change this to 2, 3, run it again, it gives me 2, 3, 4. And you'll see on the next iteration, you can see now the 4 was actually removed because it was checked to be not prime. And so now it's only 5. So the next iteration will check the last number in the list each time. And our predicate then checks, is the count equal to 1 plus the number we want? 1 plus, because we do get this extra last term. For example, if I only went through the 3 numbers here, I would have got 4 as a number. So I actually need to go to the 4th number to get the proper result. So what we actually have to do here is drop the last number because I'm going with the 1 more than we need. But that's essentially it. So, sorry, I'm trying to run that. So if I define that as a function called n primes, define, so that there is our n primes function, we can come to our first solution, which will be n primes of 101, 10,001. Sorry, n primes 1. So if I run that, you can see that gives me all the 10,001 primes, and then I just want the last one because I want the actual 10,000. So that's the actual value. So our second solution is just a small improvement on the first solution. So it looks very similar. So I'll just paste it in quick here. So everything's essentially the same apart from this plus and 2 and what we start at. So we don't actually need to do the plus and 1 as we were doing before by checking every number, because we know that apart from 2, every even number is not prime. So we're instead just checking the odds. So we're starting at 3, and then every time we increase, we're actually going to the next odd number. So the next number after 3 will be 5, and then 7, etc. But we do need to start then at 3, so we already have 2 in the list and 3. But this small improvement can actually make quite a difference to the performance, as we'll see whenever we look at the performance test. But you'll see if I define this now, it actually just works the exact same way as what we've seen before. If I run for this and you get the list of numbers again and run last on it, then we get our value. So our third solution, we start going to use the 6K method. However, rather than using it to do a check on the primes, because that is meaning that we have to check one at a time, rather than using a more vectorized method of checking the primes, we can improve the performance. So we're actually going to use the 6K method to generate the list of primes just as we had before. However, if you remember, that 6K method can generate numbers that aren't prime as well. So we'll use the 6K method to generate the list of primes and then go through that list and check and filter out the non-primes, essentially. So to do this, our starting point is going to be a 2-element list, which is going to be the value of k as the first item, and then the prime list so far. So we're going to start with 2 and 3 already known. So I define that. Then we are going to generate our list of numbers that we need to test, i.e. the numbers of the form 6k plus or minus 1. And we can do that easily, say minus 1 and 1 plus 6 times x 0, so that's 6 times k. So if I run this line, you can see that gives us 5 and 7, and then as k increases, which is going to be on each iteration, this will be the next one. So if k was 2 here, then this would be the next two numbers. So we need as well a prime test. So we're going to use the prime test that we've seen in previous videos. That's described in the blog post. I've linked in a few videos and will be linked below as well. So we're going to use that as our check. So that is defined as math in my math library called math is prime. So that is defined there, and it can be done. It can do vector form. So if I do 100 and 997, these are the numbers I had earlier. You can see it will check both of them at the same time. So what we want to do then is we want to select only the numbers that are prime in our list so far. So our list that we want to check is the numbers in this. So I say p is equal to these, and then I want to check, are these prime? Yeah, they're both prime. So we only want to select the numbers that are prime. So I say p where is prime. So it returns me only, this will filter out any non-primes. From here, if we join on to the list of primes so far, which is the second element in X, so I say X1, join this, then you can see now our list has the next prime numbers. And we also need to make sure then in each iteration that we increment our K, so we can do that using the plus a sign operator. Sorry, no, K1. So this will just increment it by 1 each time. So to put all that together, I'm just going to copy this line in and split it across 2 lines. So you can easier see it. So we have our predicate, which checks this list less than n. So at the point where it becomes greater than n, we've got enough values. So n is our number of values we're looking for. So if we wanted the first 100 primes, n would be 100. So we look at the count of the primes so far and check have we got enough primes yet? So you can see here we're just incrementing k like we did, and so that's saved to the first item of this list. So you can see the bracket matching here. This is the first item, and then the second item is what we had before, the generating the next 2 values each time with the value of k. So you can see then that this is our starting point. So if I say define n here, n is say 100, or we'll just say 10 just so we can see it. So our first 10 primes, we can run this, and you can see it is actually this returns us still the value of k, but also the prime list so far. So I count this, that's 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're actually getting one more, and that is because we're generating 2 at a time, so it is possible that we can get 1 extra. So we also need to account for that. So all we need to do here is do last to get this last list. And then we also just do n tech so that we only have the first 10, just in that case that there is an extra number. So I run that, you can see now it's got rid of the 31 and only selects the first 10. And that is our n primes 3. So I'm just going to delete all this and paste that in. So our n primes 3, you can see in functional form, looks just as we just had it. So if I define this and then run n primes 3 on 10,001 and run that, you can see that gives us our list of primes again, and our solution is just to take the last item. And again, that agrees with what we had before. Looking at performance then, you see I've got 3 solutions defined, and I've done 2 different performance tests, one for the number that we were looking for, the 10,001, and then I've also went to 100,001 just to show for a larger number. And I've pre-ran both these tests because especially the second one does take a few minutes. So having a look then at the actual results, we can see that S1 was the worst in terms of time and in terms of memory. T2, remember, was just the very small, or S2, sorry, was the small improvement of just looking at the odd numbers. You can see that it is a significant improvement over S1 in terms of time. The memory is only very slightly better. But you can see that the best solution then was S3 in terms of time and memory. And then if we look at a larger number, you can see the difference here is quite extreme in terms of the performance. So you can see it took nearly 3 minutes for one single run of the 10th or 100,001. This took 1.5 minutes, but this only took 8 seconds. So the improvement of S3 over the other 2 is quite substantial. But yeah, that's everything. Please leave your comments of your solutions, any ideas. I'd love to hear it. And thanks for watching.